For over 300 years, the Cascadia Fault beneath the Pacific Northwest has stayed nearly silent. Yet deep below, the Juan de Fuca Plate is pushing inland at up to 44 millimeters a year, steadily cranking up pressure with no release. Scientists warn this quiet could mean catastrophic strain is accumulating right now, setting the stage for a magnitude 9 earthquake and an unstoppable tsunami. But how close are we to waking this sleeping giant? And what, if anything, are today's strange tremors and sudden coastal pressure spikes truly telling us? Stretching for nearly 1,000 kilometers, the Cascadia Subduction Zone runs just offshore from northern Vancouver Island in Canada to Cape Mendocino in northern California. This boundary marks the meeting point of two tectonic plates, the Juan de Fuca Plate, a remnant of a much larger oceanic plate, and the massive North American Plate. Along this margin, the Juan de Fuca Plate is steadily moving east-northeast, sliding beneath the continent at rates that range from about 38 millimeters per year in the south to nearly 44 millimeters per year near the Canadian border. Over the course of a single year, the plates shift only about the width of a fingernail, but over centuries, this motion adds up to meters of potential movement locked deep underground. The fault itself lies hidden beneath the Pacific, paralleling the coastline and dipping gently eastward beneath cities like Seattle, Portland, and Vancouver. From the rugged Olympic Peninsula to the misty redwoods of Northern California, the entire region sits above this slow-motion collision. The immense length of the fault, roughly the distance from San Francisco to the Canadian Rockies, means that any rupture has the potential to affect millions of people across 3 states and a Canadian province. The convergence rate sets the tempo for how quickly stress builds up along the fault, providing a crucial clue for scientists as they try to estimate when and where that stored energy might finally be released. Beneath the calm surface of the Pacific Northwest, the Cascadia Subduction Zone is anything but quiet. The steady drive of the Juan de Fuca Plate beneath North America creates a slow mechanical contest, one that plays out over centuries. Not all parts of the fault behave the same way. Along much of its length, the plates are locked together, refusing to budge. Here, the relentless push of the oceanic plate does not slide past smoothly, and instead it causes the crust to flex and deform, storing energy like a compressed spring. This process, known as elastic strain accumulation, is measured by networks of GPS stations that track tiny shifts in the landscape, sometimes just a few millimeters each year. Scientists use coupling maps to pinpoint which sections of the fault are locked and which are creeping. In Cascadia, the central and northern segments, from southern Oregon up to Vancouver Island, show the highest degree of locking. These areas are accumulating strain at rates of 3 to 5 millimeters per year. Down dip, farther inland and deeper beneath the surface, the fault transitions into a creeping zone. Here, the plates slip past each other more freely, releasing some of the built-up energy through slow, silent movement instead of sudden earthquakes. The locked sections, however, remain stubbornly stuck. Over centuries, the accumulated strain in these zones grows until it eventually exceeds the strength of the rocks holding them together. When that limit is reached, the fault can slip catastrophically, unleashing the stored energy in a single, massive earthquake. The current absence of surface rupture does not mean the system is at rest. It means the spring is still winding tighter, year after year. On a cold January night in 1700, a massive surge of water battered the coast of Japan. The wave destroyed homes and boats, yet no earthquake had been felt anywhere nearby. Japanese officials recorded the event as an unexplained tsunami, later called an orphan, because its parent quake remained a mystery for centuries. It would take the work of Dr. Kenji Satake and his colleagues, piecing together samurai diaries, port records, and wave arrival times, to pinpoint the tsunami's true origin, the Cascadia Subduction Zone, nearly 8,000 kilometers away. The date was fixed with remarkable precision, January 26, 1700, just after 9 p.m. Pacific time. On the opposite side of the Pacific, clues lay hidden in the forests and marshlands of the Pacific Northwest. Along riverbanks in Washington and Oregon, stands of drowned trees, known as ghost forests, offered silent testimony. Dr. Brian Atwater and his team sampled the stumps, counting growth rings to their abrupt end. Every tree's life halted in the winter of 1699 to 1700, matching the timing of the Japanese tsunami. These trees had died not from fire or disease, but from sudden subsidence. The land dropped by several feet, flooding once thriving forests with salt water overnight. Indigenous oral histories along the coast tell of a night when the earth shook so violently that villages collapsed and the sea swallowed the land. These accounts, passed down through generations of Huayat and Makah families, align closely with the scientific record. Together, the Japanese logs, ghost forests, and living memory form a tight chronological anchor. 326 years have now passed since that night, a silence that stands out in the geological record, waiting for the next chapter to be written. Far offshore, beneath hundreds of meters of cold Pacific water, the seafloor holds its own record of Cascadia's violent past. Marine geologists like Dr. Chris Goldfinger have spent years extracting long, slender cores of sediment from the continental slope. Each core is a vertical timeline, preserving layers of mud and sand that settled over thousands of years. Most of these layers are thin and uniform, quietly accumulating as the ocean does its work. But every so often, a thick, chaotic band of sand and gravel interrupts the sequence, a marker of sudden, catastrophic movement. These are turbidites, formed when a massive earthquake shakes the seafloor, triggering underwater landslides that rush downslope and blanket the seabed in a slurry of debris. What makes the Cascadia record remarkable is not just the presence of these turbidites, but their striking synchronicity. Dr. Goldfinger's team has matched a single, distinctive turbidite layer from the base of Vancouver Island all the way to Northern California, a stretch of nearly 1,000 kilometers. Radiocarbon dating and careful stratigraphic correlation confirm that this layer corresponds to the same event, the last great rupture in 1700. No other process, not even the largest local landslides or storms, could account for such a widespread, precisely timed deposit. The turbidite evidence reveals that the 1700 earthquake was not a local tremor, but a margin-wide rupture that shook the entire subduction zone. Multiple cores, sampled from widely separated submarine canyons, all show the same event horizon. This physical record, preserved in the quiet dark beneath the ocean, confirms the scale and reach of Cascadia's most recent catastrophe, a geological fingerprint that leaves little doubt about the fault's power to fail along its full length. Deep beneath the Pacific Northwest, the Cascadia Subduction Zone is alive with signals that only sensitive instruments can detect. The Pacific Northwest Seismic Network, spelled PNSN, catalogs thousands of tiny tremors each year, bursts of low-frequency shaking known as episodic tremor and slip, spelled ETS. These tremor episodes repeat every 8 to 22 months, lasting for days or even weeks, but they do not produce the sharp jolt of a typical earthquake. Instead, they mark slow, silent slip deep on the fault, releasing a small fraction of the built-up strain. Seismic swarms, clusters of small earthquakes, sometimes appear near the edges of the locked zone, adding another layer of complexity. Meanwhile, ocean bottom pressure sensors, deployed by the Ocean Observatory's initiative, track minute changes in seafloor pressure, searching for any sign of shallow slip or sudden stress release. Yet these instruments face gaps. Offshore coverage is sparse, leaving blind spots along the trench where a rupture could begin undetected. Despite years of monitoring, no confirmed shallow megathrust slip has been recorded since 1700. Most of the fault remains silent, accumulating stress. The apparent calm at the surface is punctuated only by these subtle signals, hinting at processes that are still not fully understood. Current hazard models leave little doubt about the scale of risk facing the Pacific Northwest. According to the latest United States Geological Survey time-dependent analysis, there is a 15% chance that a magnitude 9 or greater earthquake will strike the Cascadia Subduction Zone within the next 50 years. This single number distills decades of paleoseismic records, geodetic measurements, and probabilistic modeling into a stark headline. The odds of a catastrophic rupture in the span of a single lifetime are higher than most people realize. The National Oceanic and Atmospheric Administration, tsunami simulations map the consequences with chilling clarity. In the event of a full margin rupture, tsunami run-up heights could reach 30 meters in certain low-lying coastal valleys of Washington, with 10 to 20 meters possible along much of the Oregon and Northern California shoreline. These projections are not outliers. They reflect the upper end of dozens of scenario runs, each grounded in the physical realities of the fault's geometry and accumulated stress. For communities within the inundation zone, these numbers translate directly into the height of the water that could sweep inland minutes after the shaking begins. The combination of a 1 in 7 probability and the potential for extreme tsunami run-up defines the scale of the threat Cascadia now faces. Right now, 4 million people live atop Cascadia's locked fault. With each year, silent pressure builds beneath daily life. Preparedness isn't just science, it's survival. The next rupture could rewrite the Pacific Northwest in minutes. The silence isn't safety, it's a warning waiting to be heard. Stay ready.